You are watching DHTV from California State University, Dominguez Hills.
Hi, I'm Dr. Pamela Kreiser, and welcome back to NCR 507, which is our course in Research Design and Interpretation. Now, we are going to continue to lay the foundation for the basics of research. And today we're going to talk about two very important ideas. One is to talk about basic statistical principles, and the other is to talk about experimental design. Now, as we talk about basic principles, we want to start that conversation by talking about the difference between descriptive statistics and inferential statistics. So when you think about the word and what that word means, when we use descriptive statistics, we are describing the data, or the findings in the data. And when we use inferential statistics, we're talking about inferring from the data. So it's very important that you understand the distinction, because in our world, we really use those two basic ideas very differently in terms of how they play out in research. Let's start by talking about descriptive statistics. Now, when you think about describing the data, you can think about maybe a small classroom of 30 people. And we might be interested in the demographics of that class. So we might collect data on age, we might collect data on test scores, we might collect data on ethnic background. We could do any kind of demographic variable analysis that we want, right? But if I was doing descriptive statistics, I would simply get all of those basic statistics on just that particular class, meaning that I would get the average test score for those 30 people. And I would be describing basically the characteristics of that class. So whenever we have a population that we're trying to describe, if we take the whole population and get those measures put in place and use them to describe, then that is descriptive statistics. Now, alternatively, I could use inferential statistics. For example, I might choose to take a same class of 30 people, and I might decide to get their characteristics measured on various dimensions, like we talked about, but I might infer that this class is similar to other classes, meaning that I would be inferring from that class to make assumptions about the other classes that I haven't measured. It's very important that you understand the distinction, because there's a lot of rules that revolve around inferential statistics that differ from descriptive statistics. So the first thing we want to talk about are some examples of descriptive statistics. And one of the great examples out there comes from Hans Rosling. Now, you might have seen him if you've already watched the video that's been on the discussion board previously in our course. And you'll see that he is a specialist on descriptive statistics. The next clip shows us how he covers 200 years of history talking about the descriptive characteristics of populations around the world.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health. Life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s, and in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up, Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
Hans Rosling shows us how to capture descriptive statistics on the health and wealth around the world over 200 years. Now, as we think about data and we think about how data operates in our world, it is important that we have a discussion about displaying data. Now, some of you have a background in statistics, others of you have basically no background in statistics, but you might be familiar with a common way to display data that we call a histogram. A histogram is a diagram that we use to basically describe the data that we have collected. And we use it to kind of see what's going on in the data that we've collected. This next video shows how displaying data is a decision that all researchers must make.
In this video, we will be talking about bar charts, pie charts, histograms, stem plots, and time plots. We can use these tools as a way of displaying data. We often use bar charts and pie charts to display categorical data, and we often use stem plots, time plots, and histograms for displaying quantitative data. Pie charts show the relative size of each value in relation to the whole. On the other hand, bar charts display the frequency on one axis and the values of the categorical variable on the other. You can think of bar charts as a way of tallying information. For quantitative data, we often use stem plots, histograms, and time plots to show information. We'll talk about histograms first. After collecting data from a population or sample, we can use a histogram to help us display the distribution of the data we collected. The frequency, or count, is displayed on one axis, and each count tells us how many data values fall within a predetermined interval on the other axis. This axis corresponds to the variable we have just measured. To read a histogram, you first pick one of the intervals and determine its height. So for the interval between 100 and 110, we see that the bar has a height of 8. This means that, from the data we collected, 8 people weigh between 100 and 110 pounds. For the next interval, we see that the bar has a height of 16. so this means that 16 out of the total people I collected data from weigh between 110 and 120 pounds. The rest of the histogram can be read in a similar fashion. A histogram is a form of a frequency distribution. Frequency distributions can be written in a table format, and they tell us how many data values fall within a certain interval. These intervals can be a little confusing. For example, if I recorded an individual's weight to be exactly 120 pounds, do I include them in this interval or this interval? By convention, we say that each interval does not include the right endpoint. So 120 is not included in this interval, and 130 is not included in the other interval. So in fact, 120 belongs to the second interval. Now you might be thinking, if the right interval isn't included, why don't I just rewrite my intervals like this? 110 to 119 and 120 to 129. Now the problem with this is that we don't have continuity. For example, if you weighed 119.7 pounds, there would be no interval that contains this value. Now a frequency distribution can be converted into something called a relative frequency distribution. The only difference between these two is that a regular frequency distribution shows a count, and a relative frequency distribution, as the name suggests, shows the relative frequency instead. It is called relative frequency because it represents the proportion of values in each interval in relation to the whole. To convert a frequency distribution into a relative frequency distribution, we will need to do some calculations. We start off by finding the total number of data values, and we do this by adding each frequency. We find that the total sum is equal to 50. Then, we will take each value and we will divide it by that sum. And as a result, we get the relative frequency values. To check if you have made the right conversions, you can add up all the proportions for each interval, and the sum should be equal to 1. The answer should be equal to 1 because we have used a ratio that relates our data to the total amount of data values. Because of this ratio, relative frequencies can be written in percentages. To convert to percentage form, all we do is multiply each value by 100%. In the same way, regular histograms can be converted into histograms that tell us the proportion of values for each interval. Now stem plots are like histograms, except they show each data point. Stem plots consist of stems and leaves. A leaf refers to the very last number, and a stem refers to all of the other numbers except the last number. Stems and leaves are usually separated by a line. For example, let's look at the number 117. The leaf is the last number, so this would be 7. The stem is all of the other numbers, so the stem is 11. On a stem plot, this would be written as so. Now let's look at the number 69. Using the same rules, we would get a leaf of 9 and a stem of 6. And on a stem plot, this would be written as so. Now when we have a string of leaves like this, it just means that I have the data points 30, 31, 32, 35, and 35. Notice how stem plots are constructed. Stems go down from low to high, and leaves extend outward from low to high. Depending on the dataset we are working with, sometimes we can get stem plots with too many leaves and we can get stem plots with too many stems. When this happens, we might not get a nice picture of the distribution, and as a result, we may not be able to get much information out of it. If we have a regular stem plot with too many leaves, we can convert it into something called a split stem plot. This conversion is called splitting the stems. To split the stems, we need to duplicate each stem. The first stem will run from 0 to 4, which corresponds to these values. And the second stem will run from 5 to 9, which corresponds to these values. The same logic can be applied to the rest of the stems. When we have too many stems, we can reduce the amount of stems by trimming the leaves. In this example, we have a very large dataset that goes from 201 all the way to 875. That's over 60 stems that we have to write. To trim the leaves, all we do is remove the very last digit. So notice for the number 201. The leaf is 1 and the stem is 20. After removing the very last digit, we get 20. So now the leaf becomes 0 and the stem is now 2. We would do the same process for each data value. By trimming the leaves, we get a better looking stem plot. Notice how we have reduced the amount of stems by doing this. and we have saved ourselves the trouble of having to write down over 60 stems. This is why trimming can be useful, but be careful when you read the stem plot after it has been trimmed. For example, for the top row, instead of reading it as 20, 20, 21, 22, 23, and so on, we read it as 200, 200, 210, 220, 230, and so on. This is because the original data was in the hundreds place. Now the last type of stem plot we will be looking at is called a back-to-back stem plot. Back-to-back stem plots are used to display and compare two distributions by using the same set of stems. So for example, we could compare data from males and females, or data from cats and dogs. Another way to display quantitative data is by using a time plot. Time plots show how a variable changes over time. By convention, time is always plotted on the x-axis, and the values of a variable are always plotted on the y-axis.
So one thing that we've talked about previous is this idea of categorical and continuous data. Now when I have continuous data, I have the ability to collect what we call frequency measures. And these are basic measures that you've likely heard about. But since some of you joining us don't have a background in statistics, let's go through the basics together. Now first we want to talk about the mean score, the median, and the mode. And so as we talk about these different ideas, we're reminded that the mean score is the average score, the median score is the middle score, and the mode is the most frequently reported score. Now these are interesting to me as a researcher. So anytime I collect data, of course I want to know the averages that exist. I want to know the middle scores, and I also want to know what is the most frequently reported score. But that only tells part of the story. The next part of the story is something else I want to be concerned about, and that is an aspect of what we call dispersion. When we talk about dispersion, we're asking the question, how spread out are the data? And so what I want to know is, are the data tightly collected around the mean, or are they spread out? So I'm going to look at three different areas that will help me understand that. One is range, the other is variance, and the last one is the standard deviation. You've likely heard of all of those things before. But in case you haven't, let's talk about them now, or at least remind you. When we talk about range, we're talking about the range of the highest score all the way to the lowest score. So when we think about the range, it's the top to the bottom. But when we think about the variance, we think about that also together with the standard deviation. Essentially, they are the same number. Now you might be wondering about that. Well, what is the variance? The variance is how varied the data are, and the standard deviation is that same number but in standard measurement. In other words, it's just depicted another way. Now without going into all of the specific math quite yet, which I will do a little bit in a minute, I want to talk to you about what variance is. So variance is this notion that it describes how spread out the data are. What does that mean? Well, if the data are tightly collected around the mean, or I see that I have low variance because of that, then I know that my scores are not very spread out. Alternatively, if I see a lot of variance, then I know my scores are spread out. Now, as a researcher, of course, I like the idea of variance because it helps me capture differences, something that a researcher is likely to want to find out. So as we think about variance, and of course we'll continue this discussion about standard deviation, we understand that those two help me understand whether I have variance that I've captured. In other words, am I looking at differences, or are all the answers essentially the same? I want variances as a researcher. So now let's turn our focus to talking more specifically about the standard deviation.
Have we discovered a new particle in physics? Is a manufacturing process out of control? What percentage of men are taller than LeBron James? How about taller than Yao Ming? All of these questions can be answered using the concept of standard deviation.
For any set of data, the mean and standard deviation can be calculated. For example, 5 people may have the following amounts of money in their wallets: $21, $50, $62, $85, and $90. The mean is $61.60, and the standard deviation is $28.01.
How much does the data vary from the average? Standard deviation is a measure of spread, that is, how spread out a set of data is. A low standard deviation tells us that the data is closely clustered around the mean, or average, while a high standard deviation indicates that the data is dispersed over a wider range of values. Standard deviation is used when the distribution of data is approximately normal, resembling a bell curve. Standard deviation is commonly used to understand whether a specific data point is standard and expected or unusual and unexpected. Standard deviation is represented by the lowercase Greek letter sigma. A data point's distance from the mean can be measured by the number of standard deviations that it is above or below the mean. A data point that is beyond a certain number of standard deviations from the mean represents an outcome that is significantly above or below the average. This can be used to determine whether a result is statistically significant or part of expected variation, such as whether a bottle with an extra ounce of soda is to be expected or warrants further investigation into the production line. The 68-95-99.7 rule tells us that about 68% of the data fall within one standard deviation of the mean. About 95% of data fall within two standard deviations of the mean, and about 99.7% of data fall within 3 standard deviations of the mean. The average height of an American adult male is 5'10", with a standard deviation of 3 inches. Using the 68-95-99.7 rule, this means that 68% of American men are 5'10", plus or minus 3 inches. 95% of American men are 5'10", plus or minus 6 inches, and 99.7% of American men are 5'10", plus or minus 9 inches. So, this means only about 0.3% of American men deviate more than 9 inches from the average, with 0.15% taller than 6'7", and 0.15% shorter than 5'1". This reasoning suggests that LeBron James is 1 in 2,500 and Yao Ming is 1 in 450 million. In particle physics, scientists have what are called 5 sigma results that are 5 standard deviations above or below the mean. A result that varies this much can signify a discovery, as it has only a 1 in 3.5 million chance that it is due to random fluctuation. In summary, standard deviation is a measure of spread. Along with the mean, the standard deviation allows us to determine whether a value is statistically significant or part of expected variation. Thanks for watching. See you next time.
So we've seen the importance of the standard deviation, and we understand its relationship with variance. So now we want to start thinking about an example that we could use to make it even more concrete. Let's say I had a mean score, maybe a mean age of 38 in the sample that I've collected. And maybe, just for simple purposes, I had a standard deviation of 10. That's that variance in standard measurement, right? So you might be thinking about the video you just saw, and also how we think about the standard deviation related to the mean. Of course, I look at it when I read any kind of research study. I, of course, want to look at a mean score and look at the standard deviation right next to it. And I know lots of things by just having those two pieces of information. So let's think about the normal distribution, and let's think about having a mean score of like 38. And if I went up and down one standard deviation, I would have captured 68% of my sample. What does that mean? That means that 68 of my class that I'm measuring, because remember the average age in my class was 38, 68% of the class fall between 28 and 48. And then if I go up and down one more standard deviation, I know that 96% fall between 18 and 58. Now you might be thinking, what is she talking about? How do you know this 68 and 96? Well, these are fixed principles that statisticians have given us to say that mathematically, when you go up a standard deviation, you capture 68% in that central, and then 96% with the next standard deviation. So that leads us to kind of the preliminary understanding, as you saw in the previous video, to thinking about what would be considered significant, right? Because you know in life we're going to see differences, of course, but the question is it special? And so let's say someone walked in the door to our classroom, that classroom with those data, and is 65. We would be able to say they are significantly older than the rest of the class, than 96% of the class. And if somebody walked in and they were maybe 17, we'd have the same reaction and say, no, they are significantly younger. So we use these markers to understand what's special. And it should point out to you a little bit this idea that actually it takes a pretty significant number to actually be special, because you see there's quite a range on the screen. Now, the next thing we want to talk about, of course, is the normal distribution. Let's take a look at this video.
All right, I want to show you what a normal distribution is all about in statistics. And there are three things that should come to mind when you read the words normal distribution. The first thing is that you have what's called a bell-shaped curve that basically looks like this right here. It's a bell-shaped curve, okay? That means that the mean, which is kind of sitting right here in the middle, has the most data that's sitting around it on either side of the mean. I'll talk a little bit more about that later. But definitely, bell-shaped curve is one of the first things that should come to mind when you read that word normal. The second thing that should come to mind when you hear normal distribution is that the total area under the curve is equal to 1. So all of this area underneath this bell-shaped curve, all of it, including everything out here in the tails as they get smaller and smaller, is a total area of 1. And there's one more thing. The third thing that should come to mind is that this bell-shaped picture here is symmetrical. Right? It's symmetrical. And that comes into play and is very handy. It's kind of a geometric term for later problems. So if I was to kind of split this thing right down the center here, you would see that half of this picture over here, if the whole thing is 1, is 0.5, and the other half is 0.5, giving you a total area, everything from here all the way over to here. Right, total area all together, everything under the curve here, that gives you a total area of 1. So those three things should come to mind when you hear the words normal distribution. It's bell-shaped, total area is 1, and it's symmetrical. Let me just go one more step and show you what I mean by, and perhaps you've seen this as well, not only are we talking about now a normal distribution, but something called a standard normal distribution. So a normal distribution, again, are these three things, right? Bell-shaped, total area is 1, and symmetrical. Standard normal kind of uses these three things but kicked up one more notch, and two other things, we'll mark them 4 and 5, how's that? Two other things should come to mind when that word standard is used, right? Two other things should come to mind. Number one is that the mean, and that Greek letter is mu, which stands for population mean or population average, same thing, that the mean is going to be a 0. All right, that's what standard means. Standard means that the mean, population mean, is 0. And the other thing that it means is that this Greek symbol sigma, which is a lowercase sigma, and that means population standard deviation, is automatically 1. So these two things are also part of what the standard normal distribution is, right? So there's normal distribution, which means these three things. We covered those a second ago. But when you read the word standard normal, these two things also come into play, which means, going back to this picture here, that the mean sits right here in the middle, is 0. The average is going to be 0, and that one standard deviation, right, one standard deviation in either direction is also into play. So that's what we mean, and there's this other idea called the empirical rule, but we can get into that another time. 68% of your data is sitting smack within one standard deviation. But this is what, just a real rudimentary level of what we mean by a standard normal. Means that the population mean is 0, population standard deviation is 1, and when we say normal, we mean it's bell-shaped, total area is 1, and it's symmetrical. Hope that helps.
On the most basic level, we're trying to figure out if the results that we have are really normal, like expected, or are they special? And as you think about that, that's a way for us to think about all of data analysis. This idea that, do I have something significantly different, or is it just different? Because to be just different doesn't mean that it's significant. What are we talking about? We're saying, is our finding special? And so I might find that somebody is, in the example that we did on age, somebody is 50 years old. And that might seem like old in the class setting, but it's not out of the expected range. And so we think about the standard deviation as our guide and the normal distribution as our setup for understanding what is special. Now, this next clip is going to go over the idea that we use the p-value method. And that's the method we're going to use since we're using statistical designs that are using technology like SPSS. So let's take a look at the p-value method.
All right, in this video, I want to show you the basics of hypothesis testing for the non-traditional method, or the p-value method to be more specific. All right, the p-value method. I have shown in a separate video the basics of hypothesis testing using the traditional method. So there are two different kinds. Actually, probably more than two, but I'm only showing you two in my videos. So real quickly here, the basics of hypothesis testing, no matter what method you're using, traditional or p-value, is that there are going to be two types of hypotheses, right? There's the null hypothesis and there's the alternative hypothesis. Let's see, almost every book I've used uses H sub 0 or H naught as the null hypothesis, and no matter what parameter you're talking about, whether it's a proportion or a mean or a standard deviation, the null hypothesis always uses an equal sign, right? Always has an equal sign in it. The alternative hypothesis, maybe your book uses H sub 1 or H sub A, whatever the case may be, always uses a symbol that is not an equal sign, right? So in this case, it's a less than symbol or a greater than symbol or a not equal to symbol. But no matter what type of hypothesis testing it is, you will always be given some level of significance here. Okay, so whether it's 0.01 or 0.05 or 0.10, something like that. Now that level of significance is called alpha. Right? It's called alpha, which is the Greek lowercase letter A here. That's the first letter of the Greek alphabet. So and we're not restricted to 0.01, 0.5, or 10% or something like that. It could be any other type of level of significance, but these are the three more popular ones. Okay, the other thing I want to tell you about, and keep your eye on these three alternative hypotheses here, right? So less than, greater than, or not equal to, is depending on what kind of a test we're talking about, you might have a left tail test, a right tail test, or a two tail test. And that all depends on the alternative hypothesis. So, right, so I'm using H sub 1 as my alternative hypothesis notation here. But if the alternative hypothesis is less than, we have a left tail test. If it's greater than, we have a right tail test. Or if it's not equal to, we have a two tail test. Right, we have a two tail test. So that is also important and significant here. And what do I mean by that? I didn't show this in my previous video, but for example here, let's say I've got, I got a little package here of push pins. Can you guys see that? I think you can see that in the video here now. All right, and it says that there should be 100 push pins in here. Now, if I think I got gypped, right, and I'm thinking they're putting less than 100 push pins in there, then less than would be a left tail test. All right, or maybe I'm thinking they're being generous as I buy these push pins, and they're actually putting more than 100 in. Well, more than would be a right tail test, greater than. Okay, or if I state the claim, right, all of these are claims here. If I state the claim as, I don't think they're putting 100 in there. Right, notice I'm not specifying when I say I don't think they're putting 100 in there. I believe there aren't 100 in there. I'm not specifying whether it's less than 100 or greater than 100. So in that case, it would be a two-tail test. So depending on the wording that you see, it could be one of those types of alternative hypotheses or claims. Okay, so what I showed again in a previous video, you could look it up, is the traditional method, and what I'm going to show you in this video is the p-value method. Right? But notice I wrote on this little piece of paper here that both methods, doesn't matter which method you're using, both methods require you to find a test statistic. So both methods use a test statistic. Whether your test statistic is with proportions, that would be p hat minus p, over the square root of little p times q over n, or maybe you're dealing with sample means and population means, and so your test statistic would be with this formula here. So you probably are familiar with those formulas, okay? But regardless of the method, both of them use test statistics, okay? So what the p-value does, separately from the traditional method, is this, all right? The traditional method uses something called critical values. All right, I'll just put this on here real quick. The traditional method, uses something called critical values. Well, guess what? And I'm going to cross that out. The p-value method does not use that at all. All right, p-value method says, look, I don't really care about the critical value whatsoever. So that's kind of a nice little thing here. So let's say that, for example, we were dealing with a right tail test. Right, so I'll draw a little right tail here. Right. So let's say, for example, we were dealing with a right tail test. That's our h sub 1 is a greater than. Then what the p-value says is this. All right, what the p-value says is this. What we're going to do is we're going to find, using the formulas that I just showed you a second ago, we're going to find, put here find, we're going to find our test statistic. All right, we're going to find our test statistic using that formula you just saw on the previous page, and then we're going to put that in. I'm going to write this as how about TS? All right, test statistic. We're gonna put that in here, and this is a right tail test. Let's say our test statistic here. I don't know. I'm just kind of making something up. But let's say our test statistic came out to be something like how about negative 2.61, for example. All right. Or sorry, positive. This is on the right hand side. So let's say our test statistic came out to 2.61. Okay, so for example here, 2.61. Now, do you see that this area, the area sitting over here to the far right of this, is 0.0045. Okay, you can look that up. This area is 0.0045, right? It's 0.0045, and you can look that up on a table if you want to, or you can use Excel to figure that area out. But here's the deal. That area is what's called our p-value. All right, so this area is the p-value now. All right, so the area sitting over here to the right, in this case of a test statistic, is our p-value. Okay, so that area, in this case 0.0045, is our p-value that we are going to compare. All right, we're going to compare the p-value to our alpha, to our level of significance, and that's how p-value method, the testing, works. So in our case, I have a p-value of 0.0045, and let's say that we had an alpha. Let's say that we were looking for a level of significance of 0.01, for example. I don't know, we'll pick on 0.01. All right, so our alpha, our p-value is sitting right here. Our alpha is sitting right here of 0.01. And as you compare these two, do you notice that this one here, our p-value, is less than 0.01? All right, and there's a phrase that goes along with this. If the p-value is low, right, lower than my alpha, my level of significance, then the null must go. So we're going to take the null hypothesis and we're going to reject it. Right, we're going to reject it. What if, though, let's just say, for instance, what if our p-value was greater than our alpha? All right, I know this is not the case in this particular case, but let's say we had a p-value of 0.0289 or something like that, all right? And in this particular case, look, our p-value rather, would be bigger than our alpha of 0.01. So if this is the case, if your p-value is high, right, is larger than your alpha, then the null must fly. So we're going to keep, right, the null hypothesis. So hypothesis testing is all about the null. We either reject it or we, in my case I put keep here, but technically the term is we fail to reject. Okay, so this is a reject here if the p-value is low, and if the p-value is high, then the null must fly. What we're really doing is we are really failing to reject. reject. That's what's going on here when I say the word keep. Okay, we're failing to reject. So if the p-value is low, the null must go. If the p-value is high, the null flies. And what that really means is, if we reject the null hypothesis, what we're in essence saying is we support the claim of the alternative hypothesis. Right? If we keep the null hypothesis, what we're in essence saying is this may be true, therefore we don't have enough evidence to support our claim. Right? So the wording of this is pretty tricky. You've got to get your mind around that as well. But this is how p-value testing works.
So to understand this concept in action, we need to think about the p or the alpha level. Sometimes they call it the alpha level, sometimes the p-value. We know that maybe if the p-value is 0.05, it's representing the notion that my outcome is different than 95% of the population. So think of that calculation like 1 minus 0.95 equals that p-value of 0.05. And 0.05 is going to be our standard for detecting significance. So here's how I want us to think about it. When you think about what was talked about in the video, let's identify what we say about that notion. And that's the idea that when the p-value is low, we know that the null must go. Now you might be saying, wait, I don't remember what the null hypothesis is. Remember, the null hypothesis, if I'm doing difference testing, is that there's no difference. So if I have a low p-value, that means I have a special result, and I can reject the idea that there are no differences. Now, if you're unfamiliar with that concept of the null hypothesis, you definitely need to review it in the textbook. And remember that it is simply suggesting the opposite of the hypothesis I'm proposing. So it's the opposite to what I'm suggesting. You and I are testing the alternative hypothesis that is alternative to the null hypothesis. Now let's think about the other side of the p-value. When the p-value is high, the null must fly, meaning we fail to reject the null. So my null in this case is that there's no difference. So if I have a high p-value, I'm not going to reject the null. I'm going to say these results are similar enough, meaning we don't have a special result. So make sure you take a look at this idea of the null hypothesis versus the alternative hypothesis, and make sure you understand the idea of the p-value being representative for us so that we can understand what significance is and what it isn't. Now the next topic we want to talk about is experimental design. And it's one of my favorite to talk about because it's an interesting concept for us to think about from a research standpoint. Now the first thing we talk about is this idea of true versus quasi-experimental design. When we talk about true experimental design, we're talking about the population having an equal chance of being selected. Now that's very interesting to talk about because as you and I do our measurement, we have to consider whether random selection actually happens or whether we aren't truly randomizing. If we aren't randomizing, then we have a quasi-experimental design, meaning we don't have participants that are truly randomly selected. So as you think about what the difference is between true and quasi-experimental design, I want you also to realize that when I don't have random selection, I don't have the ability to infer to the population. What does that mean? Well, if I don't think about how I collect the data, if I don't concern myself with giving everyone an equal chance to be selected for the study, then I can't make inferences from those data. So you remember earlier we talked about the idea of descriptive and inferential statistics. We have to understand that that data collection at its very core tells us what we're able to do and not do in terms of the outcomes that we can suggest from the research. So, of course, I'm going to select or suggest true experimental design. This idea that you and I give participants an equal chance of being selected. So to talk about experimental design, I want us to look at this video that talks about placebo effects, control groups, and the double blind.
In this video, we will be talking about the placebo effect, control groups, and the double-blind experiment. A placebo is known as a fake treatment. It could be known as a fake pill, drink, lotions, or any type of treatment that is known to have no medical effect. However, a placebo may have psychological effects. These psychological effects are known as the placebo effect. By believing and expecting something to work, it will work. For example, if you believe that a pill will make you feel better, then it will make you feel better, even if the pill is fake. In other words, the pill is a placebo. If you think that the same placebo will make you feel sad, then it will make you feel sad. This is the placebo effect. Placebos can be used for a control group. The control group receives the placebo as a treatment. In other words, the control group receives a fake treatment. Now, why would you want a control group? A control group gives you something to compare your results with. So suppose an unknown company were giving pills to people at the gym to help them gain strength. After 1 month of treatment, 75% of the people taking the pills report that their strength has increased. Does this mean that the pill was the cause? No. So far, this is an observational study. We cannot say for sure. Maybe there are lurking variables that are present, like diet and the type of workout routine. Some people may have better diets or workout routines, which may have allowed them to become significantly stronger than everyone else. This is why we need a control group. We could randomly assign participants into 2 groups. One group will be the control group, and the other group will be the experimental group. Each group will have to get the same thing. So each group will receive the same diet, each group will have the same workout routine, and each group will get the same amount of sleep, and etc. The only thing that is different between these 2 groups is that the experimental group receives a pill and the control group receives a placebo. A good placebo should look and taste like the actual pill. If the percentage of people in the experimental group significantly gain more strength than the people in the control group, then we can say that the pill is actually the cause for gaining strength. You can think of the control group as just doing nothing to it. We have the placebo for humans because we can perceive things psychologically. If instead our experimental units were plants, which lack a nervous system and the ability to perceive things psychologically, then we don't really need a placebo. So the experimental group of plants receives the treatment and the control group gets absolutely nothing. And then we would compare the results from the experimental group and the control group. Going back to our first example, if the control group knows that they are receiving the placebo, then this will obviously eliminate the placebo effect and it may skew the results. We need an equal playing field, where neither group knows if they got the placebo or if they got the actual treatment. To prevent bias in the manipulation of results, the experimenter should also not know which group is which. This setup is called the double-blind experiment, where the experimenter and the subjects do not know which of the groups being studied is the experimental group and which of the groups is the control group. The double-blind experiment is good for eliminating biased research results.
In our conversation about placebo effects and control groups, we want to understand that we're going to use those as comparison points to look for differences. Now remember, of course, we're talking about true experimental design, meaning we have done the work we needed to do to get a random sampling. And since we have that random sampling, then we're able to do these other things with the data. Now, what are we essentially trying to do to make those comparisons? We're trying to control for other effects or isolated effects so that they don't bother the findings that we're looking for. And so sometimes you'll see we have to hold certain variables constant. And I'm going to talk about that later in this course. The idea that you and I as researchers can manipulate parts of our study in order to try to control for influences of particular variables. So we're trying to isolate effects and we're trying to remove unnecessary effects. So let's take a look at this idea of the placebo effect a little bit closer by reviewing this TED Talk.
In 1996, 56 volunteers took part in a study to test a new painkiller called Trivaricaine. On each subject, one index finger was covered in the new painkiller, while the other remained untouched. Then, both were squeezed in painful clamps. The subjects reported that the treated finger hurt less than the untreated one. This shouldn't be surprising, except Trivaricaine wasn't actually a painkiller, just a fake concoction with no pain-easing properties at all. What made the students so sure this dummy drug had worked? The answer lies in the placebo effect, an unexplained phenomenon wherein drugs, treatments, and therapies that aren't supposed to have an effect and are often fake miraculously make people feel better. Doctors have used the term placebo since the 1700s, when they realized the power of fake drugs to improve people's symptoms. These were administered when proper drugs weren't available, or if someone imagined they were ill. In fact, the word placebo means "I shall please" in Latin, hinting at a history of placating troubled patients. Placebos had to mimic the real treatments in order to be convincing, so they took the form of sugar pills, water-filled injections, and even sham surgeries. Soon, doctors realized that duping people in this way had another use: in clinical trials. By the 1950s, researchers were using placebos as a standard tool to test new treatments. To evaluate a new drug, for instance, half the patients in a trial might receive the real pill. The other half would get a placebo that looked the same. Since patients wouldn't know whether they'd receive the real thing or a dud, the results wouldn't be biased, researchers believed. Then, if the new drug showed a significant benefit compared to the placebo, it was proved effective. Nowadays, it's less common to use placebos this way because of ethical concerns. If it's possible to compare a new drug against an older version or another existing drug, that's preferable to simply giving someone no treatment at all, especially if they have a serious ailment. In these cases, placebos are often used as a control to fine-tune the trial so that the effects of the new versus the old or alternative drug can be precisely compared. But of course, we know that placebos exert their own influence too. Thanks to the placebo effect, patients have experienced relief from a range of ailments, including heart problems, asthma, and severe pain, even though all they'd received was a fake drug or sham surgery. We're still trying to understand how. Some believe that instead of being real, the placebo effect is merely confused with other factors, like patients trying to please doctors by falsely reporting improvements. On the other hand, researchers think that if a person believes a fake treatment is real, their expectations of recovery actually do trigger physiological factors that improve their symptoms. Placebos seem to be capable of causing measurable change in blood pressure, heart rate, and the release of pain-reducing chemicals like endorphins. That explains why subjects in pain studies often say placebos ease their discomfort. Placebos may even reduce levels of stress hormones like adrenaline, which can slow the harmful effects of an ailment. So shouldn't we celebrate the placebo's bizarre benefits? Not necessarily. If somebody believes a fake treatment has cured them, they may miss out on drugs or therapies that are proven to work. Plus, the positive effects may fade over time, and often do. Placebos also cloud clinical results, making scientists even more motivated to discover how they wield such power over us. Despite everything we know about the human body, there are still some strange and enduring mysteries, like the placebo effect. So what other undiscovered marvels might we contain? It's easy to investigate the world around us and forget that one of its most fascinating subjects lies right behind our eyes.
Now you may be wondering, why are we going to all this trouble to talk about controlling for isolated effects? Well, let's observe what we've talked about previously, which is we have research involving humans. And when you involve humans in research, we know there are lots of effects to control. So when we do experimental design, of course, we're going to try to do that carefully. Now, as we think about that, I want us to review this next video that talks about randomized design, randomized block design, and matched pair design. Let's take a look.
In this video, we will be looking at experimental designs. The types of experimental designs include the completely randomized design, the randomized block design, and the matched pairs design. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. Each unit in the same group will receive the same treatment, and at the end of the experiment, you will compare the results from each treatment. Show how a completely randomized design would be used in the following example. A researcher wants to conduct an experiment to determine which environment is best suited for studying: a library, in one's own room, or outside. A total of 30 university students volunteer to participate in the experiment. So we have 3 treatments: the library, in one's own room, and outside. Since we have 3 treatments, we will have 3 groups receiving the treatments. Since there are 30 university students, these 30 subjects will be randomly assigned into 3 groups to receive the treatments. Since there are 30 people, Each group will have 10 people, and at the end of the experiment, we would compare the results from each treatment. Let's say that the researcher believes that gender has an effect on the results. In a case like this, we would use a randomized block design. A randomized block design doesn't immediately randomly assign experimental units to receive treatments. We first assign people into a block based on a characteristic that is expected to influence the response to the treatments. In this example, gender would be the blocking variable. So first, we separate our experimental units based on gender. One block will be for females and one block will be for males. There are 18 females and 12 males. Then, the experimental units in each block will be randomly assigned to 3 different groups to receive a treatment. So let's make a diagram out of this. We are looking at a randomized block design, and gender was the blocking variable. We started off with 30 university students, and we separated these students into 2 blocks. One was for males and one was for females. We determined that there were 18 females and 12 males. We will have the females be randomly assigned to 3 different groups, and each group will have 6 females, and each group will receive different treatments. For the males, we are doing the same thing, except we have 12 males, so we will randomly assign 4 males into each group. And at the end of the experiment, we will compare the results within each block. The last type of experiment we'll talk about is the matched pairs design. In a matched pairs design, we are only comparing 2 treatments by using the same or similar experimental units. If we are using the same experimental units, we could have an example like this. What type of gasoline is more efficient? Type A gasoline or Type B gasoline? 3 cars will be used in this experiment. Describe how a matched pairs design would be used. If we are using the same experimental units, then each experimental unit will receive both treatments. So we have 3 cars, and each car will receive the 2 treatments, one with Type A gasoline and one with Type B gasoline. We would use the same car for each treatment, and which treatment goes first will be random. So for example, we could drive with Type B gasoline first, then once all the gasoline is finished, we would fill up the car with Type A gasoline using the same quantity, and at the end of the experiment, we would compare the efficiency of the gasoline. There are cases when we can't use the same experimental units for a matched pairs design, and we would have to use similar experimental units. For example, a researcher is trying to determine whether or not sleep deprivation has an effect on test scores. Describe how a matched pairs design would be used. Well, we could try giving both treatments to the same experimental units, like we did in the other example. In other words, we could have the same person write the test on 2 different days, one being sleep deprived and the other with sufficient sleep. The problem with this is that we can't have the same subject write the same test because they would know what's on the exam when they write it the second time, so that would be kind of unfair. Instead, we could start off by pairing up students with similar GPAs. So for example, the 2 students with the highest GPAs would be matched up together, and the 2 students with the lowest GPAs would be matched up together. Then, each pair will be split up and randomly assigned to one of the 2 treatments. So for a pair, one person will get the sleep-deprived treatment, and the other person will get a normal amount of sleep. Then, we would compare the results for each pair, and we will also compare all of the results. So for example, if we saw that the sleep-deprived people were consistently getting lower test scores than the people who got a regular amount of sleep, then we can say that sleep deprivation was actually the cause for a bad test score. So let's quickly recap. These are the experimental designs we talked about. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. This is what the diagram would look like. Group N, or treatment N, means you can have any number of groups or treatments. A randomized block design first assigns people into a block based on a characteristic that is expected to influence the response of the experimental units to the treatments. Then, a completely randomized design is performed within each block. This is what the diagram would look like. Block N means that you can have any number of blocks that you want. For a matched pairs design, we saw 2 scenarios, one that uses the same experimental units and one that uses similar experimental units. Both of these involve the comparison of only 2 treatments. If you are using the same experimental units, Each experimental unit gets both treatments. This is what the simplified diagram would look like. If you are using similar experimental units, we first pair up similar experimental units, then each pair is split up and randomly assigned to one of two treatments. This is what the simplified diagram would look like.
As you're reviewing these videos, I don't want you to feel overwhelmed. One of the reactions that I hear often as a teacher is, wow, there's so much to know in the experimental design area. And here's what I would tell you from experience. You don't need to memorize any of it. It's all in books. So when you come upon a research problem, you can decide what you need to control for, what you need to isolate, and decide what blocking you need to do in terms of controlling your experimental design. And all of this goes to the effect that you're trying to isolate causes. You can't prove without a shadow of the doubt that a certain thing is for sure causing another thing, but you can try to assign causality. That's really what we're trying to do in experimental design. We're trying to remove the other effects so that we can see how one variable or set of variables operates on another. And we do it through very strict controlled guidelines. And as we're diligent, then we're able to isolate those effects and see them. And we do it for the betterment of the humans that we serve. So the key, of course, is to, again, return to this idea of true versus quasi-experimental design. The idea that as we're thinking about research, we want to do random selection whenever we can. Now, of course, we can't always do that. And sometimes in early protocols, like if you think of the example of drug testing or any kind of health research, we know that sometimes there are preliminary rounds that researchers will intentionally do quasi-experimental design for because of the expense of getting a true random selection. So you'll hear things like clinical trials. You'll hear notions out there of first round of research. And some of this is quasi-experimental design just to get through some of the understanding of the variables and how they operate. And then later they might follow that up with true experimental design. Of course, it's just something you need to consider as a researcher in terms of your resources and also what outcomes you're looking for. What are you trying to show? What are you trying to study? What are you trying to predict? So today we've talked about a few important concepts. We talked about some basics of statistics, which you likely knew about before. We've talked about those details like central tendency, like mean, median, and mode. We've talked also about measures of dispersion. We talked about range, variance, and standard deviation. And so in covering those basic principles, it gives us some of the building blocks we'll need as we start to get a little more into this idea of data analysis. We also spent some time today talking about experimental design. And as we talked about it, we observed the difference between true and quasi-experimental design. And then we also started thinking about block, control groups, placebo, a bunch of important features that are highly related to this idea of experimental design. So that ends our show today in terms of our work. And of course, there's lots more work to do. But as of today, we're done. So this is Dr. Pamela Kreiser wishing you a day that's not just different, but significantly different.